want to find the final velocity as well as the energy lost to friction. So when we're going to find the final velocity, we're going to look at this through a kinematics lens because we have distance as an explicit function of time. So that's why we're going to use our average velocity equation. Secondly, we want to find the energy lost to friction. So in order to do this, we're going to look at this through an energy lens because we start with potential energy, and as we move down our ramp, we have energy kinetic as well as energy lost to friction. We can find kinetic energy as well as potential energy, so that's how we're going to solve for energy lost to friction. So here we're going to try and find the final velocity of the textbook sliding down the ramp. So we're going to start with our known equations. So we know velocity average is equal to delta x over delta t. And we also know that the average velocity is equal to your initial velocity plus your final velocity. And we're going to divide that by 2. So we can say v initial plus v final over 2 is equal to delta x over delta t. And we know that v initial is equal to 0, and we're trying to find our final velocity. So we're going to go through the calculations, and we're going to say 0 plus vf over 2 is equal to, we know our delta x, which equals 1.68, and we know our delta t, which equals 2.2. So now that we know our final velocity, we're going to try and find the energy lost to friction. So we know our textbook starts up here. So we're going to say that it has potential energy at the top, and only potential energy when time equals 0. And we're going to say that it's transferred to kinetic energy as well as energy friction, because it gives some off because of the surface. So we can say mgh is equal to 1/2 mv squared plus energy lost to friction. And we're going to say we know our mass, which is 1.216 kilograms. Gravity we know is -10 meters per second. We start at a height of 0.52 meters. So we can plug those into the equation, and we can say 1.216 times 10 times 0.52 is equal to 1/2 1.216, and we know our velocity, 3 squared plus energy lost to friction.
Then it all boils down to 6.32 is equal to 1/2 1.216 times 26.
Now that we know 4.9 joules of energy was lost to heat in the transition, this is the amount of work done by friction on the book. To find that amount of work, we need to know the normal force. To do that, we switch to our dynamics lens because force is cause acceleration, and there's no acceleration in the y direction. So we know that force of gravity perpendicular equals the normal force. Doing some trig and plugging in some numbers, we found that normal force to equal 11.56 newtons. Back to our energy lens, we found the coefficient of friction to equal 0.252. Trick our units, a newton times a meter is a newton meter or a joule, and the joules cancel out, satisfying.